advance is really what I want. So laser pointing.
Oh, you have to use this.
Oh, is this one?
Yes,
All right.
Just place the space.
Oh, just the space bar.
The space bar.
All right. Let's go back one. All right. I think before I start, I would like to ask Amir's parents to stand up and be recognized, and we could show our appreciation. Would you please stand up? This is my first trip to Iran, and it's a wonderful country. We've been here for 8-9 days, had a magnificent time. So it's a great privilege for me to visit the country, and another great privilege to visit Sharif University. My first student at Stanford was from this university. It was then called Ariamer University, which may tell you how long ago I first went to Stanford. Also, my last student was from Iran, though she had emigrated to New Zealand, so she did not do her bachelor's work at Sharif, but some of you may know her. Her name was Leili Bagay-Hirad. And as we've just heard, in between those two, I had several other Iranian students, and notably Amir, whom we just had that very nice introduction to. And I think it's wonderful that you should have established a fellowship, a prize for the best bachelor's project. I am willing to offer my services as a judge of the project, if you like, Professor Kalash. So what we're going to talk about here is how to continue Moore's law. I suspect most of you know what Moore's law is, but I might go into it in detail. But if you don't remember anything else from what I'm going to say, it is important that we do continue Moore's law, because that is about how many transistors you can put on a chip. The more you can put on a chip, the easier they communicate, and the more powerful your signal processing and your computation is going to be. So I would say that it's important because what we're striving for is unlimited computation. Now, some people say that we've already got enough computation. Look at the power of an iPhone, which I don't have in my pocket, you may have, compared with a computer of 30 years ago. But we've a long way to go. It would be nice if my iPhone, or whatever, could immediately translate what I'm saying into Farsi, and even better, if I could understand your questions in Farsi in real time. That would require an awful lot of computation. So I think it's very important that we continue to strive to make better devices, and a lot of engineering goes into how these devices work. And I think Professor Fodawat is certainly one of the foremost people in the area of this technology. So that, you might say, is a summary. But now to sort of start the talk proper, I'd like to go back to the year 1960. That for me was personally an important year. First of all, I got my bachelor's degree and started working in research. Secondly, I got married, and my wife is here with us and joining me on this trip. The other reason that 1960 is important is that if you look at a curve of Moore's law, which I'm sure you have seen plenty of, and I'm not going to show you another one, is that the origin of years is 1960 and 2 transistors. 1960 AD, by the way. I'm never quite sure what calendar people use here. And of course, as you know, he then pointed out, he made the observation, this is Gordon Moore 5 years later, that number of transistors on a chip doubles every year. And that sort of show the rapid advances that we could get. I heard him talk about his law in 1977, some 12 years later. And if I can persuade this, it's the space bar, you'd say. And what he said in 1977 was, well, we've had a good run. For 15 years, we've roughly doubled the number of transistors on a chip or every year, or by then it was every 18 months. And he said, but now I think we're in trouble. I don't see how we're going to continue because it's three limitations. The circuits were getting so complicated, it was said that people couldn't design them. There were defects, so you try to make a large pattern. Those of you, I'm sure, who've ever hand-stitched a Persian rug know that you have to avoid defects. And the patterns are almost equally, in 1977, as complicated as that on a nice Persian rug. And finally, he said the lithography's in trouble. We are already down to features of the order of 5 microns, or maybe slightly less, at 3 microns. And because you're making it with radiation that's half a micron wavelength, if you want to make a well-controlled feature, it has to be several wavelengths across. Well, as we know, he was wrong. So at least we can say that smart people can be wrong. So don't worry if in your careers you say something that turns out to be wrong. Another person, rather earlier, 1969, he's a very smart person, Jack Morton. He was executive vice president for electronics technology at Bell Labs. He was responsible for developing the processes that made individual transistors manufacturable. The very early transistors, which I had a little experience of and not very happy, he made these manufacturable. And he didn't think much of the issues of integration. He said 64 bits, not kilobits or megabits or megabits are that. He said just 64 bits because we're already working with yields that are about 30%. And if you take a look at a random array of dots, and this is an array of chips on my Excel spreadsheet, these are the defects you might expect to get if the defects are randomly arriving with an equal mean value. It's the Poisson distribution. And as you may know from the Poisson distribution, the chance of getting an area free of defects goes down exponentially with the area. So he said it's clearly hopeless. What he got wrong was that, in fact, the defects do not occur as a Poisson distribution, and indeed, there are many variations that they have. And for instance, I've shown one here, such that there's a greater mean probability down here than up to the top right. We call that the stationary, or non-stationary, distribution of defects. And now you can see we've got a few die that are yielding. So that really helped greatly in increasing the scale of integration. And indeed, the person who really killed the defect problem, well, I shouldn't say kill, but showed us how to attack it, was Professor Omi and his team at Sendai University, Tohoku University in Sendai in Japan. That's the one that got hit with the big earthquake, but I'm happy to say that the university buildings were strong enough to withstand it. For instance, up to that point, yields of 30 or 40% were regarded as economically attractive. But after his work, it was 80 or 90% that the Japanese were manufacturing 1 megabit DRAMs. So that leaves, if we can get to it, lithography. One of the ways that you can scale Moore's law is simply trying to cram them sideways, you might say, by shrinking the dimensions. This, for example, as you probably recognize, is a SEM cross-section of an MOS transistor, so that your gate up here is controlling the current between source and drain here. This is shown at one size. If you scale the dimensions by a factor alpha, obviously everything gets smaller, but in fact other things, parasitic capacitance and resistance decrease. But you have to apply a lower voltage, because one of the rules of the scaling is that the fields have to be constant. The doping is increased because the depletion layers also have to decrease in size. And if you do the sort of fairly elementary calculations, you can find out that the power dissipated is given by CV squared times the frequency at which you're running the transistor. This means that you can either reduce the power of a circuit by shrinking, or you can increase the speed at which it's running, or some combination of the two. So this led to an explosion, a huge effort in trying to make things smaller. And indeed, another saying I heard from Gordon Moore about the year 2000, he said, everything gets better as we go smaller. So the cost of the exposure tool became of concern. Even in 1975, the cost was 0.1 megadollars, or $100,000. By 1985, the first step and repeat cameras became available. They cost $1 million. Outrageous. People said it would clearly be uneconomic. But in fact, those tools have evolved until today. It will cost you $60 million to purchase one of these state-of-the-art stepper tools from ASML or from Nikon. But the extraordinary thing is that these very expensive tools work so fast and make so many fine features that in fact the cost per minimum feature that you make has also gone down dramatically. So it makes sense to spend $60 million if you can drive your cost per feature that's patterned down. But you may notice that the slope is beginning to level out here. And I'm going to go into a bit as to why this is. You may notice that ends at 2010. If you extend it to today, you'll find that curve is almost flat, and we're beginning to think it might start going up, in which case the advantage of shrinking features might well decline. There may be other more technical reasons why transistors with ever smaller features will also work properly, and that's an area of great activity, one which I will not get into, but if you want specifics, again, talk to your professors Fodawat and Kalaj, and they will be happy to tell you all about it. But certainly, these evolved devices are working. But as I said, that curve is leveling off. We're now, as I say, getting stuck because optical lithography is being driven. We've dropped the wavelength from 400 nanometers to less than 200 to 193. And indeed, instead of needing many wavelengths to make one well-defined feature, these people have managed to drive it to 1/6 of a wavelength. So 1/6, that's about sort of 30-something nanometers. And they've used all kinds of techniques. For the analytically inclined, you might think of trying to make an image by controlling, say, the amplitude and phase across some wavefront that is converging on the wafer. If you want to make just a single point, of course, on a spherical wavefront, you would simply have a constant amplitude and constant phase. But if you're trying to make an IC pattern that might have 10 to the 10th, 10 to the 11th minimum features, that's a huge field of view. It would make any digital camera that you or I could afford look stupid. Then it becomes a computational nightmare, or you might say job security for the algorithm people. So there have been all kinds of ways they can cheat, and they are trying their best. But then you might say, well, why not go to electron beam lithography? It has finer, much finer resolution. You can resolve 1/10 of a nanometer in a good transmission electron microscope. And so this is an area which I've been heavily involved in. And you might say, a fair chunk of my career was proving that this wouldn't work. And the reason is that electrons, as you may know, repel one another, and if you start to push enough electrons through to expose the resist in an economically fast enough manner, the repulsion, the space charge effects, will introduce aberrations and will defeat your purpose of trying to get high resolution. I will show, I think, one side of the EBL, because there isn't a way that you might get around that. This is where the industry has placed all their bets. EUVL, does anyone know what that stands for? Well, if you know, you're not saved, right? Okay, EUVL stands for Extreme Ultraviolet Lithography. Now they call it that because there was an earlier industry-wide program on X-ray lithography, which I suspect some of you may remember. And the industry worldwide spent probably a couple of $1 billion trying to make X-ray lithography work. And for reasons I won't go into, it didn't. But it left a very bad taste about the words X-ray lithography. Now, extreme ultraviolet lithography works with a wavelength of 13 nanometers, which to most of us, we'd simply say that's a rather soft X-ray. But they couldn't call it soft X-ray lithography because of the unhappy connotation of connection with the earlier disastrous project on X-ray lithography. But if you want my honest opinion, or even a dishonest one, we're just having history repeat itself. They have sunk several $1 billion into this, and it's still not ready. So the unfortunate thing is that I'm missing something. Doesn't matter, I know time is short. People discovered that printing would be very effective, mechanical printing. Do you know how a CD is made? Anyone know how a CD is made? Again, if you know, you're not talking. You simply take a template that has the indentations corresponding to your music or whatever you're listening to on a template, and you have on your disc, if you like, a thin layer of a plastic, like a photoresist or any other resist, and you simply squash the thing in there, and it makes very fine features. A CD has features of the order of about 1 micron to half a micron. And you can check that, and I was going to show you. In there, if you can get the CD out, and you can pass it around, and you can see that you can get a diffraction picture of it. Now that is the CD, is it? Or is that the DVD? That's the CD. All right, you can play with this, but what you can do is you reflect off it, and you ought to be able to get 0 order and the first order, which means that the spacing of the grooves on here is about 1 micron, because the wavelength of this laser pointer is 650 nanometers, about half a micron. Why don't you pass it around and people can play with it, because they love playing with laser pointers instead of listening to me. By the way, Mr. Chairman, what time am I supposed to finish? About 4 o'clock?
About 4, yeah, about half an hour. 4 or 5.
Ah. All right, I will try not to bore you. By the way, I should thank you for showing up on what is a holiday week for many of you people. In fact, the first Nowruz I attended was with Amir many years ago. So nanoprinting, a professor at Minnesota, Stephen Chow, discovered that you could extend this idea of nanoprinting. And we will omit that for now. It's not going to advance. Well, we'll try it. Well, I think I better ask Professor Collage to see if he can get this to work.
Want to go ahead, forward or back?
Oh, let's keep going. Oh, you managed to make it go forward. We'll skip this. That's all in the optical lithography. Actually, we can, no, go forward one if you can. That's where it gets stuck.
Okay.
All right, now advance it if you can. No, it's going backwards. Fine. I'll take over from you. Yeah. This I'm showing simply shows how design has evolved. When I was working at Bell Labs on lithography, 1970s, the designers were king. We, as lithographers, had to do exactly what the designer wanted. If there were curves, diagonals, star-shaped, we had to deliver it. But thanks to the increasing costs of the lithography tools, our status as lithographers increased because of the expense of lithography. And so what we worked on was making the features easier to make. So initially what we finally said is, well, we can make gratings. We can make gratings very finely. We have ways of doing it. For instance, there's something called double exposure patterning. I'll try to, oh, do you want me to?
Yes,
I hope my voice was
yeah.
raucous enough that let's leave it there. Okay. I thank you. Yeah. This is a sign lent to me by Jan Borodowski. He was the chief of lithography at Intel, and what he has done is to develop techniques that is what we call double exposure. Now, the thing about the resolution that you may know of a microscope or of any optical lithography technique, this projection, is that it is the period that is limited by Rayleigh's law. If you then make a period of gratings where the bars are spaced more widely, narrower than the spaces, then on a second exposure, you can come between the two. So you just move the wafer by a tiny fraction and make a second exposure. You've now doubled the frequency of your pitch. Of course, it only works for gratings. So this shows you, for instance, that he has doubled once and then doubled again. So he's done 4 exposures, and he's got minimum features here. Well, the pitch is 28 nanometers, so the lines and spaces are each 13 nanometers. And he's done this with a wavelength of 193 nanometers. That is just extraordinary, but again, it's only a grating. So I'll see what we can do with this. Now we'll forget that. Let's keep going. That wasn't what I wanted. All right, I will just explain it. So we can make gratings. Then what you do, you look at the gratings on the wall there. And then what you can do is a third level of lithography, maybe lower resolution. You just cut the lengths of it. Let's see if I can find that one. How do you go backwards? I seem to do that quite effectively before. That's it. No, one more. Yeah, there we go. So this is done with the, you can't read the printing there, the 65 nanometer node, and these are some of the features that we're making. This is the 32 nanometer node, half the distance. Now you see, what they've done is they've made the grating patterns. It may be a couple of levels of exposure, and then with a different tool, they've simply cut these things to length. So now the device designer, the circuit designer, has to work out ways in which they can make a fully functional circuit using these very simplified patterns. That's what they're doing at the moment. So now we will go ahead. doesn't it? It doesn't like this going ahead from this one. You should have kept. That's it. Oh, is he taking his time? Yeah. So I was talking about nanoprinting. Professor Chow at Princeton discovered that by using the same technique as making a CD, the squashing technique, that you can get really fine features. And he demonstrated 10 nanometer features just with one single squash of a tool that doesn't cost anything like as much as the $60 million for a stepper. So I think this is a great way of going. Can we? Okay. It doesn't like that one, does it? So, the trouble is that the industry is committed to extreme ultraviolet light and are putting all the money into that, and they haven't put any into the nano imprinting. So the nano imprinting is showing some really impressive results. Again, let's keep going. We seem to have an order problem. No, it'll come, I think. Yes, here we go. So these are some imprint features. And these were done on what is now a commercially available machine. Again, just squashing. They've got features here of a 16 nanometer half pitch. You can say it's pretty good line width control. The EUV people would, I don't know if you understand the word, drool if they could do this. And just as a tour de force, goodness me, we've got an 11 nanometer half pitch, and although you can't see it on the screen, I'm not quite sure why not, we'll try once more. Yes, we got it. These are replicas taken with the same technique of simply imprinting. They've used a single wall carbon nanotube, 2 nanometers across, and we've got a replica of it in the plastic. This is the work done by John Rogers and his team at the University of Illinois. And I cannot understand why the industry is tending to ignore this. But the main point is that these techniques do exist. I think what I am not really competent to talk about is the attraction of going even smaller. But it appears to be a way that people, I don't see what, because as you make things smaller, down to a point, things start to come and hurt you. The interconnects, although they might be shorter, the resistance per unit length increases. You can just do this with simple algebra. And L and C per unit length remain the same. So for the same cross-sectional area, you'll get the same characteristic impedance. My feeling at the moment, it may change, is that we ought to go to 3D. So we don't have to have these very expensive lithography tools, and you simply have to learn to put one layer on top of the other. As you know, we're doing this already with the passive, the wiring. But what I think would be attractive is if you could also stack your transistors. And that turns out to be not very easy. But I think it's going to happen. Oh, skip that for now. It's going to take its time. And that. It's going to take a little time. Come on. So let's go backwards again. Bye-bye. Now, you might say that's pretty obvious. You pry open your iPhone if you feel like doing that, and you'll see that there are chips stacked vertically. So you might say that's one example of vertical integration. And they tend to be, the simplest ones are connected to 2 levels around the edge. All right, let's keep going. Can we move forward?
Yeah, I'm trying.
Oh, you're trying. All right. I should have prepared something to say about these, but we're running on time. There is another technique that people are trying, is you make your circuit, say, on one wafer level, and you make the next circuit level on an SOI wafer. Do you know what SOI stands for? Good. Silicon on oxide. So as you have a very good single crystal level of silicon on top of a layer of silicon dioxide, and then there's the main substrate. So you make the second level on this wafer, you put it on top, and then you manage to separate by, say, dissolving away the oxide so that the bulk of the top wafer comes away, but it leaves the circuitry on the original wafer. And there are people doing that. Let's keep going. So I'm looking at the time. So this is the pitch I made. So chip stacking, I said, is already here. It's edge connected. You can also, in fact, do array connected through what they call through silicon vias, or TSVs. That's now coming into commercial use. Then the one I was just talking about, the SOI wafers, is being looked at by various people. IBM, you might say, have projects on almost anything. So, but this is a small company, MIT Lincoln Labs, and this is largely on Department of Defense research money. But even that seems to me too crude. What I'm really trying to do, what we have, is to make what I call a monolithic, so that you might, for instance, be able to put down single crystal silicon on an amorphous substrate. And that's a fair challenge. But there are various ways of doing it. Let's try this go. Can we go ahead? We are trying. Okay. The key to how good your 3D circuit is in fact how dense you can make the vertical interconnects. Because we like to make them as dense as we can for the metal. So you've got wireless communication, you can get away with a very low via density, as they say. And then you can get down to about 10 to the 6th is the monolithic approach, because we know we can make features that are certainly 200 nanometers across. Let's go ahead. Thank you. This shows a cross-section of some of IBM's work. This is a coarse, very coarse via structure, and here you can go to a much finer one. So let's keep cranking. Thank you. Oh, haven't got there yet. Is it taking it? I think you've got a virus in this computer. This is the Tesron approach that I just mentioned. So this is the original wafer with its active devices on the top layer of the silicon. And then they have these very thick, this is the layer then of the silicon on oxide structure up here with its circuitry on top. So you essentially have two fabricated circuits and you connect them with these very thick pads here. And so this is, you might say, an honest attempt to go a bit further. This shows an SEM shot of the Tesseron structure. So these are some of the levels you saw with the transistors at the top and the bottom of this particular cross-section. This shows how they didn't quite get the alignment right, but it's all right, they're making contact. But you can see there's a little kink there, indicating the two layers weren't quite right. Okay, let's see if we'll still go ahead. This is what I would like to get. So this is, in fact, the cover of a proposal we sent to the Department of Defense, where I'd like to be able to put all our transistors, unlimited number of levels, and there's reason we think we can do it, because this shows, in fact, a nice single crystal diffraction pattern, then a layer of amorphous oxide, then another layer of nice single crystal material. In this case, it's germanium and that is silicon. So we felt it could be done, but we did find difficulty in putting down the single crystal islands. Because what I'd overlooked, and it was a stupid mistake that I made, was I didn't think that you could, how shall I say it? When you have transistors and a complete circuit and you put stuff on top, you're limited in how hot your processes on the second layer can be, correct? Any idea how hot you can make things before things start to give trouble? Are these graduate students in the device area? A few of them, all right. It's about 400 degrees. So you have to then heat in a different way, or put them down in a different way. Now, Philip Trunagorek was one of my students, and he came up with a technique that's not unlike the Tesseron approach, except that you don't have any circuitry on the top layer. You just put down isolated islands of, he would put polysilicon, he could also do single crystal, and this was an array that he made. And so if you can now put your circuitry into that, because these are quite big, that's a 50 micron bar. So how about the next one? Another student, Bipin Rajendran, who's now a professor back in Mumbai, said, all right, steady state heating we're limited to 400 degrees. But if you use a laser, you can do flash heating at the top, so that you can activate the dopants in the source and drain of the top transistor, which is the critical heating step. And the heat, by the time you've activated, you can flip off the laser, and the heat hasn't had time to get down lower and cause trouble. So he showed how you could make 2 layers of silicon MOS transistors, both N-channel and P-channel, and I think that's a very attractive way of going. We haven't got around to doing it. So another form of 3D stacking is with NAND technology. The nice thing about flash memory, particularly NAND, is it gives itself very well to making contacts, simply essentially dropping what you might think of as an elevator hole or post hole through multiple layers. So they're claiming that they're making 128 gigabit 3-bit levels, MLC multi-level cell, for the NAND chips. There's some discussion about whether they're making them with economic yields yet, but that is another example of how 3D is coming in. All right, I'm checking time, we've got 5 minutes. So let's move on. The other thing people complain about 3D is they say, look, if you stack your transistors, they're all dissipating heat, and you're going to have to get rid of an awful lot of heat, and the heat also has to get down to the whatever is your heat sink. And the heat sink better be pretty good. So I'm not sure if Professor Fodawat ever knew my student David Tuckerman, but he and I, and particularly he did, realized that if you shrank a regular heat sink with fins and channels, it worked very much better because you're compressing, as you make these channels finer, you're forcing the boundary layer to be smaller and smaller. And as a result, the convective heat transfer is very, very good. Or to put it another way, on the very first night we made this, we were dissipating 800 watts in a square centimeter of silicon, and we still weren't boiling the water that was going through. That was remarkable. That was roughly, well, a little later, we actually got to 1.3 kilowatts being dissipated in a square centimeter of silicon. And getting rid of it with the water flowing. So I think that's a very attractive way of going. There's another interesting thing which we didn't exploit at the time, is that the thermal time constant, you can leave this, was about 30 milliseconds. So you can heat something up and cool it down in 30 milliseconds. That has various applications. And the one I've been trying to investigate, and this is what I'm doing right now, is to see if you can use this technique of locally heating your substrate, monitoring the precision with which you're overlaying two areas, so that we can now get the overlay in the nano imprinting process completely accurate. So we use the technique of Tuckerman and made an 8-inch wafer chuck. We can go to the next one. It's trying, is it? So this is an 8-inch wafer chuck, and in the chuck, which is a piece of metal, we have now put in an array of microchannel heat sinks, such so that you can in fact vary the temperature locally, either by changing the temperature of the water flowing through these, or in fact by an external lamp. We can see the next slide. This shows a, is it coming? Good. This is thermal images, again, of the 8-inch wafer, and obviously the yellow stuff is hotter than the darker purple. So this is just illustrating that we are able to, where did those crosses come from? Ignore those crosses, just look at the yellow patches to show that we can selectively heat different areas. So the very first experiment we did, we are trying, was didn't even in fact use the microchannel heatsink. We just used a metal plate initially because I was having trouble with my plumbing. And Dr. Moon has a technique for using quite inexpensive microscopes for sensing the overlay between two gratings. He claims he can get an accuracy of less than half a nanometer. So initially our project was to then see how well we could stabilize the dimensions, the overlay over this area, simply with two sensors, go into a computer, and then go into a programmable power supply, which control the lamp, that control the heat here. So let's look at the next slide. In the first, will she come? Here we go. So what we're showing here is the distance, or the overlay error, of 2 points about 2 inches apart, using those two microscopes over a 30-minute period, and this was just with open loop. So just the ambient air as we have in this auditorium, air blowing all over the place. And you can see we're getting fluctuations of the order of plus or minus 50 to 100 nanometers. Then he switched in the feedback control, and then he was able to get a stability of roughly plus or minus half a nanometer. I mean, it worked right out of the box. It was really very exciting. So here we have, right away, remarkable control. Now the next thing, could we do it with multiple zones? So this is the second experiment. Now I've solved my plumbing problems. We've got now our microchannel heat sinks, and we have 3 wafers, 2 regions here. The issue is, could we get the whole thing stabilized so that we had accurate overlay at each of these points of the kind of accuracy we saw. And if it will come up, it will be. So we wanted independent control. So these are the plots now of the distance or the overlay error as a function of time, 30 minutes. This is for the left-hand zone, and this is for the right-hand zone. And what we're seeing is little in fact, remarkably good. Holding, apart from these little blips here, I'm not sure if in this country you have water coolers the way we do. But our problem was when we first used a pump to pump the water through the microchannel heatsink, that caused enough vibration that we couldn't use it. The water flowing simply, when it's pumped, the little pressure pulses, doesn't work. Look rather like an electrocardiogram. So then we made a gravity feed using a water cooler on top of a cabinet and just had it going through our microchannel heatsink and getting, and then we tried the experiment, but we were still getting little blips. And what we found that was being caused by is the water coolers we have, if we get a cup of water out of them, usually then a bubble goes up through the reservoir. Do they have those water coolers like that here? So it turned out that these blips are being caused by the bubble going up through the reservoir. So we've clearly got a little more work to do, but nonetheless, we say that the 3 sigma, we're not giving a value for X, but it's the order of half. So it's 0.5 nanometers roughly, is 3 sigma. Again, remarkably accurate. So I think that is, let's keep going, if you will. We're trying. So, yes, we should keep Moore's law going quite a bit longer. It's important that it does continue, and what I've not shown here is that we've got a number of ways of continuing it. We're able to make features that are 11 nanometers across. We can overlay them with a precision of less than a nanometer. And we have all the tricks that the optical people are doing. So you can overlay, and the next thing is to get the defect count down. That's how we do it by squashing. And then, of course, there's the 3D approach, which I also think is an attractive way of going. So yes, there's a lot of work to do. I mentioned that the NAND technology and a lot of that flash memory technology is very different from the logic technology. This is something that's happened gradually over the last 20 years. So the scaling laws are more for the logic type of technology. But there's a lot of exciting things we can do with memory. There's magnetic techniques, there is phase change, and so there's a lot of really exciting device work to be done there. So I look forward that you are going to make the advances long after I have ceased to be conscious. So thank you very much. I'd like to wish you all a very happy Nowruz, and thank you for coming to this talk. If there are any questions, I'd be happy to do my best to answer them. I know it's very difficult to ask questions to be the first, but maybe he's going to ask a question.
No, actually I'm going to try to help in questions. همونطور که ملاحظه کردیم آقای پروفسور پیز تو زمینه لیتوگرافی تخصص دارن و ماکرولیتوگرافی و ملاحظه کردیم که از نظر ایشون وقتی که ما راجع به مورز لا صحبت میکنیم صحبت این هستش که به پایان مورز لا که رسیدیم چگونه مسیر رو ادامه بدیم. ما ملاحظه کردیم که چجوری تلاش کرد که به اصطلاح نوارهای خیلی نازک بتونه درست بکنه با طول موج نور که از ابعاد نانومتری دیوایسی که میخواد بسازه بزرگتره. و همینطور مسئله دیگه‌ای که ایشون بهش اشاره کرد در مورد به اصطلاح 3 دیمنشنال کردن مدار بود. ملاحظه کردیم که ایشون گفتش که اگر ما اینا رو بخوام رو هم استک بکنیم، گفتش گوشی اپلتون رو اگر که باز بکنیم ملاحظه می‌کنید که آی‌سی ها رو هم از کناره ها استک کردن. یعنی یه آی‌سیه که پایه های چند تا به اصطلاح تراشه است که رو هم نصب شدن، از کناره ها به هم وصلن و تراشه هایی که به اصطلاح از وسط هم به هم وصل باشن. اما اینکه واقعا بخوایم تراشه به اصطلاح مدار سه بعدی داشته باشیم. ایشون توی یکی از اسلایداش نشون داد که توی استنفورد این کارو کرده و اومده روی یه لایه آمورفوس، یعنی روی سیلیکون دی اکساید مثلا یه لایه کریستال سیلیکون دیپازیت بکنه که رو اون دیوایس بسازه و مشکلی که وجود داشت این هستش که اونجا دما از 400 درجه بالاتر نمیتونست بره و برای همین ایشون از لیزر استفاده کرد که بتونه دیوایس رو لوکالی به صورت ناگهانی بدون اینکه حرارت به اصطلاح منتقل بشه قسمت‌های دیگه دیوایس رو بتونه گرم بکنه و روی این ساختار سه بعدی بتونه ترانزیستور بسازه. حالا عرض کنم که من زمانی که در خدمت ایشون بودم when I was there a student at Stanford, his student David Tuckerman was there, and it was at that time that they started to pass water through silicon wafers. I just did a small summary of what you said to help them in asking more intelligent questions. In Farsi, we can summarize a 1 hour talk in 2 minutes. No, just joking. Okay. Any questions? Any questions? بفرمایید. میکروفون وایرلس یه چیزای کوتاه آقای برنامه رو فرستادن دنبال چیز نیست. شما بفرمایید من تکرار. So what she said, she's actually a PhD student in superconductivity, and her question is, if we have multiple layers of devices, you showed 2 layers, and she says if we have multiple layers, what is the solution for transferring the heat from the middle layer to the higher layers?
That is a very good question, and I will ask. Do we have a blackboard or whiteboard? I don't believe we do.
Yes, we do have a whiteboard here, but it must be somewhere.
Let me describe it. One of the reasons that the monolithic is effective is because you can make the vertical thickness smaller as opposed to the prefabricated designs. So I would like to suggest that you could do a calculation of supposing we had 10 microns of SiO2. And down here we had the Calculon-G's heatsink that could get rid of roughly 14 watts per centimeter squared per K. That is the specific thermal conductance at the bottom. So your question is, how do you get the heat to it? And I'm saying that if you make it thin enough, and 10 microns is pretty thick by nanotechnology standards, I think you will find that because you made it that thin, that the heat conductance of the Si2 is enough. It's even helped because, of course, you have vertical wiring as well. On the other hand, you might argue that we don't use SiO2, we use aerogel for a low K material for the interlayer dielectric, and in which case you can revert to COMSOL or some other finite element technique, and you can do a numerical calculation, which we did do. In fact, some of the students of Subhashish Mitra did some calculation. I think we reported it at some point. I was very interested to hear that you're working in the superconducting area. Let me put it this way. David Tuckerman, before he came to Stanford, was working on the IBM superconducting computer project. And that project was justified on the grounds that silicon could not dissipate the heat. And when Tuckerman joined my group, he asked me, do you think that that's a justifiable reason for superconductivity? Do you really think silicon can't dissipate the heat? And we did some elementary calculations. I said, well, supposing you had infinite heat sink on the back of a thin silicon wafer, it just turned out we could dissipate 30 kilowatts in a square centimeter. Whereas the folks at IBM were claiming you couldn't get rid of anything like that amount. And the IBM project was in fact discontinued within a year of our publication. I like to think that we were part of that decision. But I think superconducting devices for special purposes have a really good place. But I don't think it's in computation myself. But I'm willing to debate that. Thank you for asking a question.
سوال دیگه در مورد این بالاخره کسی فهمید که چجوری روی ویفر سوال بفرمایید.
Many thanks for your talk. I'm keen about the calculations for your conductances in the thermoconductance devices. Okay, you think the layers, but in between the layers we have capital boundary resistance or acoustic mismatch impedance. Isn't that, because in our works normally that is the limiting factor. Isn't that the limiting factor in your devices?
So you are getting an interface,
Yes,
getting
the
reflection of the phone
impedance of the interface normally is much higher than...
Yes, the interfaces are a problem. Ken Goodson, who has done quite a lot of calculations on this, indicates, yes, that is a problem, but it doesn't look like it's so serious, it will kill us. But it depends what you're doing on the upper layers.
Yes.
And in particular, the vertical vias, particularly the ones that deliver power, are quite thick. And so, in fact, the calculations, I should confess, of Mitra's people indicates that most of the heat goes through the power delivery vias. Yeah. Thank you for that's a very good point.
Thank you.
I'd like to ask a question. On this slide, you showed that with existing equipment at Samsung, IBM, Sematech, and Toshiba, they have been able to go to minimum feature sizes of 16 nanometers.
Yeah.
And then you mentioned that, is this Professor Rogers at Illinois, who went down to 0.4 nanometers. What I was wondering is, this is just a lithography technique that does that, and if you're able to do that, then you're able to do metals with this type of feature, and also to use diffusion.
Yes.
Okay. Can you explain again the technique for the 2.4 nanometer?
I hope you weren't going to ask that question. My understanding, this is what I imagine he did, was he put some carbon nanotubes on a glass surface, got an imprint of them, was still able to observe the carbon nanotubes after he separated the replica. And these are the pictures, I believe. That's the master, that's the replica, so it is kind of dirty, you might say, but on that feature, it was a tour de force, I think, of technology.
آقای دکتر سروری متوجه بشن که چقدر کاربران تو کار جالب میتونه بکنه. سوال دیگر، سوالای ادمیشن و دانشگاه استنفورد رو نمیدونم به اصطلاح اینا مجازه ها. Just wondering, I just said questions about admission to Stanford are also allowed.
Yes. I can say that because I'm retired, so I'm not the admissions chair any longer.
But there is one student you're supposed to interview today. He's already sitting here, you're supposed to interview.
That's excellent.
Actually, I have a question about the dimension of the TSVs. So you told that in a monolithic integration, you are using two silicon layers, okay? So how large are your TSVs? Because it can literally impact the design partitioning approach. I mean that if we can implement small TSVs, so we are free to design our whole system in multiple layers and we are not limited with the number of TSVs. But when we have large TSVs, so the number of TSVs are limited on achieved and the granularity of the design partitioning should be large. I mean, the diameter, for example, how many micrometers or nanometers?
If I think I understand the question, I'll give my answer. I picked very, you might say, crude models. And as we discussed, if you make the vias very fine, then the power distribution becomes difficult. There is a problem on, do you know what is meant by the L, di by dt noise?
Okay, yeah.
When you suddenly switch, the whole power and ground levels might change. So you need to have fairly thick vias for power delivery.
So it's limited partitioning granularity of the design. I mean, if you have large TSVs, so you should have a whole system in one chip or in one substrate and another system in another substrate. We cannot partition, for example, one transistor in one layer and another in the second layer. I mean that you are limited with local interconnect in each layer and only a global one between layer. True?
Yes, those are all very good points. Did you say she got admitted to Stanford?
No. Oh, yeah, that's good.
Come and talk to me afterwards.
No, she was already a faculty member.
Oh my goodness, these people look so young. So come and have a sabbatical leave at Stanford. You can help with the 3D project.
Thank you.
I'm not really a designer. I believe in Subhasish Mitra and his students. But very good question. Yes.
Okay. من فکر کنم آقای دکتر سوال شما رو خوب نفهمیدن چون احتمالاً گوششون درست متوجه نشده. در نتیجه فکر کنم باید بیاید آخر سر دوباره. سوال دیگه بفرمایید. خودم این برسه. میخوای بیاید جلو؟ میخوای بیاید جلو که خودت سوال رو بکنی؟ بفرمایید.
Again, thank you very much for your complete and understandable presentation. I have a question about this slide. In this slide, it is shown that the transistor can be implemented in top layers
Yes.
or top levels. Does it have any advantages, or is it applicable, for example, for better performance, or is it just an experiment?
It will not be better performance, but the fact that you can put them on an upper layer makes the design problem much more. It gives more degrees of freedom for the design to be able to put stacks of active devices as well as simply stacking the wiring. Because now, for instance, you have a very long wire, you could in fact put an amplifier repeater along it.
So you mean that it is not applicable for applications, different applications, is not yet applicable, yes?
Well, only insofar as having three-dimensional stacks of transistors gives you more freedom.
Okay. Thank you very much.
یعنی در واقع بیس تکنولوژیست که بشه باش بعدا استفاده کرد. بفرمایید، خواهش می‌کنم. تشکیل شده.
اگه میشه من از شما بپرسم شما.
باش.
من صبح از ایشون تو دانشگاه همکاری پرسیدم که آیا مدل‌های فالت و دیفکتی که توی دنیای تستینگ سنتی وجود داره میتونه جوابگو باشه. ایشون هم گفتن که نه، حتما نیاز داریم که مدل جدیدی ارائه بدیم. من حالا تازه فارغ التحصیل کارشناسی ارشد شدم. میخوام فکر کنم این سوال ازشون بپرسم که این چقدر میتونه واسه من امیدوار کننده باشه این طرز فکر من واسه دوره دکترا که کار کردن، تحقیق کردن، فکر کردن روی این موضوع.
اول من سوال شما بفهمم، شما منظورتون در مورد این اسلایده که ایشون دنسیتی دیفکت ها رو روی سیلیکون نشون داد و بعد گفتش که همه فکر می‌کردن که به اصطلاح بذار من به اون اسلاید برم که توزیع دیفکت ها یونیفرم باشه، ولی بعد معلوم شد که توزیع دیفکت یونیفرم نیست. راجع به این دارید صحبت می‌کنید؟
بدتر از توزیع نوع دیفکت ها، مثلا دیفکت مثل استاکت و کراستاک و اینا توی تراش‌های دو بعدی وجود داره. اینجا هم شاید وجود داشته باشه، شاید انواع دیگه از نوع دیفکت هم بشه جورای دیگه مدل کرد، دیفکت‌های دیگه جورای دیگه بشه مدل کرد. این مدل سیام میتونه وجود داشته باشه با توجه که من فیلدم هاردور سکیوریتی هست. از دیفکت‌های موجود استفاده می‌کنم واسه کشف مثلا تراشه‌های آلوده، بعداً تراشه‌های قرار باشه در مرحله فابریکیشن برسید مثلا پارتیا.
Okay. Here, if I can reword what he's trying to say to the best of my ability, you mentioned that you have a uniform distribution of defects, and then it turned out that the defects were not uniform, and that helped in increasing the yield.
That's correct.
The other question, he's taking the issue a level higher. He is asking, when we talk about defects, we are talking about defects in the crystal structure, and
No, I'm talking about dust particles.
dust particles.
Yes.
What he says is that we also think of defects like when we look at the circuits in terms of logic circuits, where we have a stochastic logic, or we have basically he wants to relate the dust particle or the crystal structure defect to the circuit, and he wants to know if there is any opportunity in that area for future research at PhD level.
That's this one works?
Yes.
Yeah, very interesting. Here, as we said, we referred to dust particles. This is one example of the false arguments that Jack Morton were coming up with, which stopped Bell Labs essentially working on integrated circuits for a time. I've showed this example as one. Another very frequent. You have to decide what do you mean by yield. In the research lab, if we can get a circuit to work in a very narrow window, that's all right. We can publish our paper and move on. But in any industrial setting, a device to work, a circuit to work, it has to work over certain windows of the power supply levels, temperature, humidity, stress, or whatever. And so you put your circuit through all those tests, and you find that things like the threshold variation might be rather slow across a wafer. So yes, I think in the terms of the crystal structure and defects, any help you can give us on the upper levels would be greatly appreciated, because the laser flash annealing that I talked about It is an awkward process. But if you can help us get zero or acceptably low crystal defects in the upper layers, that would be very exciting indeed. Thank you.
خب من فکر کنم کفایت بکنه. تشکر بکنیم همه. We thank Professor Pease again, and if you have individual questions, he's going to be around for a couple of minutes, and I think you're welcome to come to the front here and have your own personal questions. Thank you very much.
Thank you.